Linear regression. One of the most powerful ideas in all of machine learning, and one of the simplest. By the end of this video, you'll understand exactly how it works. At its core, linear regression answers one question. Given an input x, can we predict an output y? Input x might be how many hours you studied. Output y, your exam score. Or x is a house's square footage, and y is its sale price. Or x is today's temperature, and y is how many ice creams get sold. In every case, we have data, lots of x-y pairs, and we want to learn the relationship between them. Let's trace through a real example, step by step.
Here's our data set. 15 students. Each dot represents one student. Their x-axis position tells us how many hours they studied, and their y-axis position tells us their exam score.
Notice something already?
As study hours go up, exam scores tend to go up too. That's a linear trend. Our goal is to capture that trend with a single straight line and use it to predict scores for students we haven't seen yet.
We could try just drawing any line through the data. Too steep? Nope. Too flat? Still wrong. Getting closer, but still off.
What we want is the line of best fit, the one that comes as close as possible to every single data point. There it is, and it's described by a simple equation, y equals mx plus b. Let's break that down. Y is what we're predicting, the exam score. M is the slope, how steep the line is. Slope equals rise divided by run. For every extra hour of study, the score increases by m points. B is the y-intercept, where the line crosses the vertical axis. Even with 0 hours of study, B gives us a starting baseline score. For our data, the best fit values are y equals 6.8x plus 29.9. That means every extra hour of studying predicts about 6.8 more marks. Example, 8 hours. Plug in 8 hours, 6.8 times 8 plus 29
equals 84. The model predicts a score of 84. But wait, how did we actually find those specific values of m and b? How did we know 6.8 was better than 5 or 9? The key idea is measure how wrong we are. For each data point, we compare the actual score with what the line predicts. The gap between them is called a residual, or an error. Teal is above line, coral is below line. Some residuals are positive, we underpredicted. Some are negative, we overpredicted. We square each residual. This ensures everything is positive, and it punishes large errors much more than small ones. Then we average all the squared errors. The result is the mean squared error, our cost function. MSE equals 1 over n, sum of y sub I minus y hat sub I squared.
The lower the MSE, the better our line fits the data. Our goal is clear. Find the values of m and b that minimize the MSE. Enter gradient descent. Imagine the MSE as a landscape, a bowl-shaped valley. Every point on the horizontal axis represents a different choice of parameter w. The height at that point tells us the cost for that choice. We start somewhere random, up on the slope. We want to roll down to the bottom. At each step, we look at the slope, the gradient, and take a small step in the downhill direction. The update rule is w minus alpha times the gradient of MSE with respect to w. Alpha is the learning rate, how big each step is. Too big and we overshoot, too small and it takes forever. Step by step, we inch toward the minimum. Ball reaches minimum, flash. And when we get there, we found the optimal
M and B.
Gradient descent iteratively nudges M and B until prediction error is at its absolute minimum. And now we have a working model. Want to predict a score for a student who studied 3 hours? Plug in x equals 3. The model gives about 50. 7 hours? Score of around 78. All you need to do is plug any x into y equals 6.8x plus 29.9, and you get an instant, data-driven prediction.
Linear regression. Simple, powerful, everywhere. Step 1. Collect paired data. Step 2. Fit the best line using gradient descent. Step 3. Use that line to predict anything. This single idea, finding the line through your data, is the foundation of machine learning. Master it, and everything else becomes clearer.